Welcome to this session on drilling optimization, well-designed process to execution. This is submodule 1 of 4, where we will walk through the entire process of moving from well design all the way to execution. Our focus is on understanding the key steps, risks, and controls that ensure wells are delivered efficiently and safely. Over the next series of slides, we will break down each component, explore the concept of drill in the box, and highlight how safe operating windows are defined and applied in real operations. This submodule sets the foundation for applying digital tools, procedures, and risk management to ensure consistent and optimized performance. Let's begin by looking at the objectives for this module. In this submodule, our learning objectives are clear. First, we will develop a thorough understanding of the complete well-designed to execution workflow, from geological evaluation all the way to operational delivery. Second, we'll explore the concept of drill in the box, which provides a structured way to define boundaries and operational envelopes. Third, we'll learn how to establish safe operating windows by integrating rig capabilities, tool limitations, and fluid properties. Finally, we'll look at how well programs are delivered, covering not only the technical procedures, but also associated risks and execution planning. By the end of this session, you should have a structured view of how design decisions translate into executable drilling programs. With that roadmap in mind, let's move into the first stage of the process, design to execution. The phrase design to execution captures the complete journey from concept to well delivery. Let's watch a short video on Drill Plan's drilling intelligent workflow.
For well construction, over the last 5 years, we have built a fully connected set of planning and operational solutions, which are cloud native and are built on open standards. We collaborate across domains from geology, geomechanics, and well integrity, all the way to field development, and in the future, intervention and production. Our customers are realizing the value of automated engineering and validation, which drives efficiency and quality of the plans. Digital plans are then consumed by our edge solutions, where automation today is reducing well times by more than 20%, making better decisions, reducing tool failures, and reducing non-productive time. Our predictive analytics solution drives drilling performance through drilling optimization and risk mitigation. Now, our customers will generate more learning and insights from data and feed this back into better operational decisions and lessons learned for the next well, so each well is better than the last.
The well design process is multifaceted, and this slide lays out the building blocks. We begin the well design process with G and G, geology and geophysics. This stage establishes the foundation of our design by characterizing the subsurface. We integrate stratigraphy, geomechanics, petrophysics, and seismic data to build a model of the reservoir and surrounding formations. The accuracy of this data is critical, as every downstream decision is based on these inputs. Next is trajectory design, where we translate geological targets into a drillable well path. Here we account for location constraints, the shape and position of the reservoir, geomechanical stresses, and drill string or rig limitations. The trajectory must balance technical feasibility with safety and cost efficiency. Once the trajectory is defined, we determine casing seats. These are depths where casing strings must be set to isolate problem formations and provide structural stability. Geomechanical sensitivity and formation-specific challenges often drive this decision. Moving forward, drilling mechanics come into play. This includes fluid design, drill string configuration, hydraulics, torque and drag analysis, and vibration control. Each of these factors is optimized to ensure smooth, efficient drilling performance. Following this, we carry out the casing design, ensuring it can withstand downhole pressures, mechanical loads, and safety factors. Tubular availability and floating equipment are also considered here. Next, cementing design is developed. This involves calculating volumes and pressures, ensuring thickening times are suitable, and verifying that compressive strength builds adequately to maintain zonal isolation. We then specify other equipment, such as rig sizing and solids control equipment, ensuring they are adequate for the well's requirements. Finally, we build the procedures, the operational roadmap. This includes time forecasting, compliance with API and IADC standards, and risk management. Importantly, the process is iterative. Each step is revisited and refined as new information becomes available. Together, these steps ensure that the well design is technically robust, operationally feasible, and ready for safe execution. Next, we'll explore the drill in the box concept, which frames these constraints visually. This illustration shows the K and M depiction of the drilling in the box concept. It represents the safe operating envelope where drilling can proceed efficiently without exceeding equipment or formation limitations. The box captures the interaction of mechanical, hydraulic, and operational parameters, and it serves as a visual tool for engineers and drillers to stay within safe boundaries. We start with the mechanical parameters. On the bottom plane, we see RPM, hole diameter, angle, and drill bit selection. These directly influence torque and drag, as well as how the bottom hole assembly behaves. Increasing RPM improves rate of penetration, but can also introduce vibrations, while hole angle and bit type affect steerability and cuttings transport. The hydraulic parameters sit across the top plane, flow rate and mud rheology. These govern hole cleaning efficiency, pressure control, and cuttings suspension. Poor rheology or insufficient flow rate can reduce hole cleaning, increasing drag and risking stuck pipe. In the center of the box, we have BHA design, mud type, and percentage of sliding. These represent controllable design choices. The BHA affects directional response and stability. Mud type sets fluid properties for wellbore stability and lubrication. Sliding percentage indicates the directional drilling mode, which directly impacts torque, drag, and tool face control. Finally, on the right-hand side of the box are performance outputs, ROP, and torque and drag. These reflect the result of all the input variables. If parameters remain within the box, drilling progresses efficiently with manageable torque, controlled drag, and optimal penetration rate. Exceeding the box boundaries, however, leads to instability, high mechanical loads, or loss of wellbore control. The value of this concept is that it transforms a complex multi-parameter system into a simple visual framework. It guides decision-making in real time, ensuring drilling stays within safe, productive operating limits. Planning and operations are often viewed as separate stages, but in practice they are deeply interconnected. The goal here is to link the design process to execution in a seamless loop. Planning provides the technical foundation, trajectories, casing programs, fluid designs, and risk assessments. Operations then bring these plans to life on the rig. What's critical is feedback. Lessons learned during operations must be captured and looped back into planning for future wells. This creates a continuous improvement cycle where execution informs design and design evolves to prevent recurrence of past issues. By connecting these processes, we ensure consistency, reduce risk, and capture value across the drilling program. Next is a short video on the drill plan auto engineering process.
So now the trajectory design has been shared across the team and it's going to be ingested in all the other engineering workflows, from casing design, kick tolerance, hydraulics. So now everyone in the team is working from a single source of data. So I want to show you now the automated engineering analysis. This you can see here is the validation dashboard, where you can visualize your entire well design throughout all the hole sections. It has automated engineering analysis for hydraulics, torque and drag, casing design, kick tolerance, and more. So this analysis is using all the designs and details that the entire team has shared. So every time there is a change in a design, the automated engineering analysis will recalculate all the results. This is over 30 engines running automatically on the background, and it will validate your results again. So it will let you know if you have a coherent program, and it will warn you if you not. It will also give you recommendations on how to improve your design, and you can easily identify where you need to interrogate with more detail.
Defining a safe operating window is essential for risk management. This window represents the range of drilling parameters, such as mud weight, pressure, and RPM, where operations can proceed without exceeding equipment, formation, or tool limits. Accurate data is the foundation. The more precise our geomechanics, fluid properties, and tool specifications, the closer our defined windows will reflect reality. Key considerations include tool limits, rig constraints such as pressure handling and circulation capacity, fluid properties, and drill string dynamics. Any misalignment in these can close the window and increase risk. This method of defining constraints helps us avoid catastrophic failures and keeps drilling within manageable limits. On the next slide, we'll apply this concept with a practical check your understanding exercise. The illustration is an SPE reference plot showing weight on bit versus RPM. Different shaded regions represent safe and unsafe zones. Tool limitations, shock and vibration effects, and wellbore stability are indicated on the chart. The design also combines the limits for maximum design weight for the bit, the limit for hole cleaning, and the top drive torque limit. Also added are the ROP contours, and in the shaded areas the zones where the onset of vibration from stick slip, forward whirl, and backward whirl. The more stable the BHA design, the larger the white area will be, which is the stable drilling zone. Poorly designed BHAs have narrow operating windows, resulting in suboptimal drilling performance. Using finite element analysis from software tools such as Ideas or iDrill enables proper design and improved drilling performance. When drilling automation tools such as SLB's ROP Optimizer continue to recalculate the safe drilling window and recommend parameters to maximize performance. By practicing this, we build the habit of defining and respecting limits before risks escalate. With this foundation, we can now move on to how design is delivered into execution through standard deliverables. The video clip shows ROP Optimizer working in real time. The system's limits have been added for bit, top drive torque, and steerable motor hydraulics. The system simulates drilling according to the recommended parameters provided by the software. On the right shows both the parameters used by the driller would make without the optimizer recommendations. The center column shows the difference in the performance. Delivering a design into execution requires structured documentation, and that's where the WELL program comes in. A WELL program is the master document that translates design into step-by-step procedures. It contains casing points, trajectory details, bottom hole assemblies, fluid design, and a full time and cost summary. These elements ensure everyone involved has a shared reference. Risk analysis is also a critical component. A high-level HAZOP, or Hazard and Operability Review, identifies potential risks and ensures mitigation measures are planned. These are derived from offset history. This structured approach prevents oversights and creates a culture of accountability. Once the program is in place, digital platforms such as DrillPlan further enhance delivery, ensuring the program is accessible, standardized, and easily updated. Next, we will show a short video on the digital drill plan creation process.
So now all the team has shared their designs to DrillPlan. Each design now can be assigned to be digitally reviewed and approved by the relevant manager or domain expert or senior engineer. In this case, we can see that the drilling manager has received a notification to review the activity plan. So she can visualize all the details of the design. The activity plan is prepared on drill plan by using all the relevant offset well information, and it automatically calculates the estimated time per each activity throughout the well construction. So it also has customized templates for standard operating procedures notes throughout the activities. So she reviews it, and now she can decide to digitally accept it or reject it. So in this case, she accepts. Then after the final digital reviews and approves have been done, just with a simple click, you can print your fully customized drilling program through the collaboration now of all the whole drilling team. And it saves hours of administrative work.
Let's take a moment to review the objectives we set at the start of this submodule. Our first goal was to understand the complete well design to execution workflow. We achieved this by stepping through the design process, from geological inputs to casing, fluids, drilling mechanics, and final procedures. The second objective was to explore the drill-in-the-box concept. We saw how defining operational boundaries provides a clear framework for safe, efficient drilling, and how staying within those envelopes reduces risk. Third, we set out to define safe operating windows using rig, tool, and fluid limits, through plots of weight on bit versus RPM, and by considering rig capacity and wellbore stability. We demonstrated how to apply these windows in practice. Finally, we focused on delivering well programs with procedures, risks, and execution plans. By examining the standard deliverables and the role of drill plan, we showed how design is translated into execution with clarity and accountability. Together, these objectives have given us a structured, practical view of drilling optimization. In the final slide, we will formally close this submodule. That concludes submodule 1 of 3 on well design process to execution within drilling optimization. Please proceed to the quiz to test your understanding of the key concepts we've covered. Thank you for your attention and participation, and I look forward to continuing with you in the next submodule.